Hi everyone, do you see my screen?
Yes, we do. We can start.
Okay. Sorry for inconvenience. My name is Shant. I'm leading a computer vision group of computer vision scientists at PicsArt. Also, I'm giving lectures in Yerevan State University on computer vision topics. Today we will talk about attention mechanism and Page-based techniques in computer vision, and also we'll talk about an application in image painting problem. So what is visual attention? In our daily life, we often solve some tasks, for example, crossing the street or reading something or searching some items in our environment. For this, we need focus our attention on some part of the information we get. Roughly speaking, attention is a mechanism for selecting a specific part from the whole visual information we get from our environment. Let's consider the task of identifying someone in a photograph. For example, let we want to find Niels Bohr here. How do our brain works? We focus on some people and iteratively until we recognize Niels Bohr here. So,
sorry, Shant, it seems like people don't see the screen. I do, but not everybody does.
Okay. I will stop.
Can you please stop and start again?
Mm-hmm.
Please, participants, now that Shant will share the screen again, write in the chat or in Q&A chat, whatever, whether you can see it or not.
Now it's visible.
Yeah, it seems now it seems
okay.
to be visible to everyone, hopefully.
Okay.
If you don't mind, you can go back and just skim through the slides.
I will start from the beginning. So, what is visual attention? Now, daily life we use our visual attention often, and for example, when we want to cross the street or read something or find an item in our environment, we need to focus our attention on some parts of the visual information we get. Let us consider the task of identifying someone in a photograph. For example, this famous photograph of the conference in 1927, where many scientists of the 20th century were collected together. And we want to identify Niels Bohr here. How our brain works. It searches over people and focusing at each of them or on some of them until we recognize the person we want to identify. So the question arises, besides the information we get from the part of the image we are focused on, what kind of information helps us to identify where to focus at the next steps? The answer is that we also use the part of the image of the visual information we did not focus on. So the attention mechanism can be defined as assigning importance values or attention scores to the elements of the visual information we get. This meaning of attention we will use in computer vision and to define the attention mechanism. But at first, let's begin from the origins of this concept. The attention mechanism was introduced for neural machine translation problem where we have the input sequence x1, xt, and we want to get the output sequence yt. By encoder, we get feature sequence h1, ht, and decoder produces the elements of the sequence yt. Decoder at each step iteratively uses the information from the previous step, and also it uses a vector, so-called context vector, which pay attention on all the outputs from the encoder. But at each step, this attention score differs from the other steps. This is done simply by taking weighted average. Without going into details in this paper, I would like to emphasize that in this algorithm, alpha ij's are also computed iteratively. So at each time we get this context vector, we need to compute new attention scores for the next one. The other concept of self-attention, which is more close to the one we use in computer vision, was introduced in the paper "Attention is All You Need," and this model is just a function with which takes three inputs, three matrices as inputs. Let's assume these matrices have the same dimensionality, and outputs another matrix with the same dimensionality. For simplicity, let's assume all matrices are of the same dimensionality. So what does this model? For each row qi, which we call query, if query from the Q matrix, we compute all similarities with the inputs from the key matrix, and these similarities will indicate our attention scores, which we apply to obtain the output CI. CI is just a weighted sum of elements in the value matrix. And weights are calculated as similarities between the eth query vector and all key vectors. The intuition behind. For each vector qi, we want to formulate an output ci. And we want to output ci pay attention on all vectors from V. And we want ci to pay more attention on those values Vj, for which the query qi is more similar to the keys kj. Now let's talk about the self-attention in computer vision. A very similar approach, just generalizing for 3D tensors, was introduced in the following paper, Self-Attention Generative Adversarial Networks. They use this concept for style transfer problem, about which we will talk a bit later. In a sense, this mechanism takes the input X, produces query key and value tensors by using one-to-one convolutions. And computing some similarities in the same way as we did for the two-dimensional case. And after that, we take the weighted sum of Vj's with using these similarities. As in the previous case, here we also take for each I, we take eth query QI compute its dot products with all key vectors and compute softmax over it in order to interpret the values Sij as probabilities. So if we interpret these values as probabilities, we can see that our output is just the expectation of taking values Bj. So here I would like to mention that the index I stands for pixels, for each pixel, not for each row or column. So it goes from 1 to h times w. Another version of attention can be used if we instead of taking the expectation of values, we just random sample with from these values with the probabilities Si1, Sin for the ETH output I. This kind of attention is called hard or in style transfer problem. There is a paper which introduces the style swap algorithm, which is in a sense a patch-based method to swap the patches from the content image to the with the patches of the style image. Let's investigate the style transfer problem described in a solution described in their paper. For those who is not familiar with the style transfer problem, there is two inputs, content image and style image. And the algorithm needs to produce a stylized image with the style of the style input and the content of the content input. Let C and S be the content and style images respectively. We feed them to an encoder. It can be pre-trained with G encoder or something else. This is a fully convolutional encoder, and output some three-dimensional features. Let's, for simplicity, assume that our C and S images are with the same dimension, with the same size, and we obtain phi C and phi S corresponding features in the same dimension, with the same dimension. So the main idea is here in style swap operation. In a sense, it takes all k patches from both phi C and phi S, and let's denote these patches by phi C and phi S. We will have h times w patches for each feature map, and for each content patch phi C, the algorithm finds the best matching patch among the patches of the style feature. After finding the best matching patch, we simply replace the source patch phi C with the best matching patch from the style tensor. Of course, in case of replacing patches, we will get some patches overlap and aggregate these overlapping parts by averaging. So this operation is called style swap because we are replacing patches of content tensor with style tensor, and we produce with a nice result like this. Also, I would like to mention that here, instead of taking the best matching patch, one can take some close patches, several close patches, and randomly sample from them, which is done for the next algorithm. If we use these patch-based techniques for texture synthesis or hole filling. Let's assume we have an image and missing region here. Here is missing region, and we want to fill this hole coherently from outside of the hole. For these purposes, we take the boundary of the hole. We consider all patches which are centered in this boundary, find their best matching patches, and replace them and aggregate these overlapping parts by averaging. Here, instead of the previous case, when we use similarity as a dot product between normalized patches, here we use just Euclidean distance between known parts of two different patches. And also as there, here we can randomly sample the matching patch from several similar patches. In a sense, it is the same as stochastic attention, but not pixel level, but patch level. Indeed, in this case, we can just take query key value tensors as the input and output the tensor. And for each patch of the output, we can sample from the outputs of the patches of value tensor, and sample with probabilities we are assigning to each patch. In the simplest case, when we use just the best matching patch, the probability of the best matching patch will be equal to 1, and the probability of other patches will equal to 0. The advantage of this technique over the simple pixel level attention is that this is done with patch level, and this helps us to keep structure continuities even in deep features of neural networks. We will show it later. So now let's talk about imaging painting problem. What is imaging painting problem? This is in a sense the same thing as hole filling in images. We have an original image. We want to remove some part of this image, or we want to fill some missing regions in this image. Then we somehow identify the region which we want to fill or which we want to remove, and want to output a result like this. Application can be removing unwanted objects or text, recovering scratches or torn parts in all photos, or face completion, etc. Let E be a colored image, the input image. And here we want to remove some parts which are identified by a binary mask. Ones here indicate the missing region. And we want to get such output. The existing approaches to this problem are divided into two groups: patch-based methods and learning-based methods. One method can be the one which we have discussed. By the way, in this, in case of this image, the algorithm we have discussed applied directly on the image can produce also good results. This is because patch-based methods have the advantage to recover texture. Sometimes they complete texture parts perfectly, and also they are good at structure propagation from the outside of the hole to the inside. But there are some drawbacks concerning semantic inconsistencies. For example, if you want to use patch-based methods for completing the missing part in face, you will end up just with nonsense. Because, for example, if eyes are missing in the face image, and patch-based methods can never recover them because there is no information which can use patch-based method to recover this part. Instead, in contrast with these, learning-based methods can produce semantically meaningful outputs, since they can generate new content which is not present in the image with the missing region. But learning-based methods are bad at texture completions, and they introduce some blur artifacts or patterns. Recently, some algorithms try to combine these methods and do both: output semantically meaningful images and make texture make more detailed textures. Our approach is also in this manner. We train neural networks, a new neural network which composed of two consequence models. One stands for coarsely estimating the filling region, and the other stands for refinement, this coarse estimation. Our main idea is in our coarse network. Here by the yellow part you can see, and we identify the patch-based method I have talked about. The network takes these two inputs, the image with missing region and the missing region, and produces this coarse output. Our module with patch level attention allows us to preserve structure continuities from the outside of the hole to the inside. Here are some comparisons and examples. Here we compare with two state-of-the-art methods, one with partial convolutions, the another with gated convolutions. As you can see here, partial convolution introduces some patterns. Gated convolutions cannot distinguish the parts of trees and grass, and our method can preserve the feature continuities, the structure continuities. Here is the same with structure and pattern, and more examples. Also, we would like to compare with a recent method, recurrent feature reasoning for image painting, which was presented a few months ago in CVPR. We have chosen this method because they also use the iteratively completing the missing region in deep features as we do. But in contrast with us, they use not partial level similarities, but they used pixel level similarities and pixel level attention. And by this comparison, we would like to mention that using partial level similarities will produce results which keep feature continuity, structure continuities. And here also the same. So that's all for talk. Thank you. If there are some questions, please ask.
Thanks a lot, Shant. I'll monitor the questions, and if there will be any, I'll ask. And before that, I'll try to ask a question from my side. So first, it's pretty amusing to see how the ideas from NLP, for example, with its self-attention, transfer so easily and effectively to vision, to computer vision. And the question is, I guess, the following. So in case of self-attention for Inpainting, The number of queries is equal to the number of pixels that are blacked out.
Mm-hmm.
Is that the case?
So
For each pixel which is blacked out, you have a query, right?
as we fill the hole iteratively in the features, for each iteration, we have the boundary of this hole. So the number of the queries is equal to the number of pixels in the boundary of this hole.
And you gradually move inside the boundary.
Yes, yes, yes.
That means it should be much slower than ordinary gun, which predicts right away the whole area, right?
Yes, you are right. This operation is slower, but if we do it in deep features, we can it gives us some speed because the number of queries and also the key elements are less than if we will proceed this procedure directly on image.
Okay, so you can't directly transfer this to production because of the slowness, right? Or
I suppose we can because it is, of course, it is slow, but it is not so slow that we cannot do it, for example, in a resolution 64 and 64 when the input is 512 and 512.
okay, there are two questions in the chat, but the time actually is out already. And can you see the question and answer section of the chat, Shant?
Mm-hmm.
If there's one question that you can really answer briefly, the answer of which won't take a lot of time, you can try. Otherwise, people are welcome to ask the questions in the Slack channel.
The first question is, do you use positional encodings? Actually, no, we don't use positional encodings, since in patch level attention, the neighborhood of the pixels are already considered. So we didn't use positional encodings. And the second question I will answer shortly. How do you evaluate the goodness of the results? Well, in the image imprinting problem, of course, there are some metrics to evaluate the goodness of results, but these metrics are just PSNR, SSIM, or recently the metrics, perceptual metrics LPIPS was introduced. But actually, for image painting problem, there is no a data set with inputs and ground truths, with objects and removing version of these objects. So we just use the original images and try to reconstruct them, and we measure metrics between the original images and our reconstructions. The metrics are PSNR, SSIM, and LPIPS.
Thank you for the answers as well, Shant. Thanks again. This was the last talk of the day, but we have also a panel discussion today, and I highly recommend you to join that panel discussion. The panel discussion is going to be about the vision topics. This type of panel discussions often are can be very fascinating thanks to the freestyle nature of those talks.